So welcome everyone. Thanks for joining this talk. I'll start with a brief introduction of ourselves. So my name is Hoyoung. I'm the lead data scientist at Think Data Works. So I've joined this company in the beginning of this year. And our team, Data Labs, is trying to understand and solve the most common problems in data science. My previous work is mainly focused in NLP applied research to solve conversational agent problem for smartphones and automotives.
Hi everyone, my name is Cheng. I'm currently studying at McGill University, and this past summer I worked at Think Data as a data science co-op, specifically working on entity resolution.
So our talk today is about building a flexible framework for entity resolution and our journey towards making information more available and accessible for everyone. So entity resolution is probably not the most well-known problem in NLP space, but we think it's a very important one. This talk is mostly focused on how entity resolution can be applied in practice. So by the end of this talk, I hope everyone here is more familiar with the problem and hopefully potentially apply it to your work in the future. So in modern business, each team operates as an independent unit. And so they decide to manage their own database for more agility. So the end result is data silos. Data silos are the source for the most common data problems, such as duplicates, incomplete data, and inconsistent formats, and so on. As of June 2019, we now have over 4.4 billion internet users. This is an 83% increase in just 5 years. And still today, data scientists spend 80% in data preparation and only 20% in obtaining actual knowledge. And we think this is a big problem. So entity resolution is the task of disambiguating different representation of the same real entities across data sets. In this example, you can see many different variations can exist in data, but when there's only a few unique entities in real world. And there are different terms for entity resolution, such as record linkage, deduplication, fuzzy matching, and entity matching, and entity clustering, but really they all come down to the same problem. This talk will just use entity resolution to be consistent. So entity resolution is a classification problem. We want to classify each entity pair E1 and E2 in Cartesian product across data set D1 and D2 into a match or a non-match. When D1 is equal to D2, it becomes a deduplication problem. So from the tables, you can see examples of structured data, and textual data, and dirty data. And most entries in open data, it's still entered by a human. And so it ends up being very messy data with inconsistent spacing and typos and wrong column and use of abbreviation, etc. So due to time complexity being O(n) squared, there are blocking mechanisms to reduce the search space, meaning using columns like age to create multiple search blocks. However, blocking requires clean and structured data, which is usually not the case for open data today.
So this past summer, I helped with a lot of the development and logic of the entity resolution system that Think Data Works currently offers to our clients called ER². So I'm going to be walking through a couple of the applications of ER, but this isn't an exhaustive list. It's just the specific applications that the interface of our product makes really accessible to our users. So the most intuitive application of entity resolution would just be deduplicating a data set. So given some sort of table with a specific column that you want to deduplicate off of, you can run entity resolution on it and find which specific rows or entries in this table correspond to the same entity. And the way that our ER² sets it up is that each entity is assigned an entity ID, which is appended as an extra column onto the data set. So for example, the first and third row might have the same, in column B, might reference the same company, for example, but it's formatted slightly differently. So they get the same entity ID, and we pass back this final table to the user for them to decide what to do with it. So if they did want to just clean their data so that they had a data set with only unique entities, they could just select the unique IDs. So once we can find duplicates across one data set, we can extend this to multiple data sets and actually achieve intelligent linking across data sets. So this is a slightly more powerful application of ER because it enables merging data sets without unique keys. So going back to the data silos that Hoyoung talked about, obviously when you have a bunch of different databases, they might be formatted differently even if they're within the same company. And if you want to merge all of the information you have within these databases to have one source of truth that's more meaningful than just these data silos, you need to be, without entity resolution, you would need to have some sort of unique key to join off of. But with entity resolution, we can actually run ER on all of the data contained within both of these to find the duplicates across the combined data sets within the two tables. And for example, E1C here, so the top entry in column C, might point to the same entity, or it might reference the same entity as E3D and E4D. And so when we run entity resolution, we can find that these actually correspond to the same entity and then use the fact that they reference the same entity to join the two tables. So in the end, we get an end table that's more meaningful because it has more of the knowledge consolidated. However, if we look at the table that's produced, obviously not all data silos are going to have the same information for all the same list of entities, and we might end up with empty tables. And it's not necessarily the most meaningful representation of the combination of all of the knowledge available to us. So a more meaningful one would actually be using a graph where every single node represents a specific entry, and every single edge corresponds to a type of relationship that you gain. So to give a concrete, simple example, we could have one table of company names and all the employees that work at that company, and then we can have a second data set that has company names and then the addresses. And if we wanted to link these using entity resolution in an intelligent way, we could do that and end up with a table of where each individual, of the address that each individual works at. So this is a simplified example of how we can aggregate different tables to gain more meaningful insights, and entity resolution enables that. So all of this can sort of be combined into one giant application of master data management. So once we can find duplicates within a bunch of data sets and find a way to aggregate all of this information, we can build a master data management system that allows us to take a bunch of different data silos or databases and use the knowledge in the most efficient way possible. So if we have an effective entity resolution system and then we have an effective ranking metric looking at how often specific instances of the entities appear. So maybe Acme Corporation is the version of Acme company that appears the most. We can assign each group of duplicate entries with one unique ID and one representative entity name and have that correspond to our understanding of that entity. And then we can rearrange all of the data that we have and consolidate it in a way such that all of the other relationships that we know from the other databases related to one single entity is preserved. And so we can aggregate all of our knowledge into one consistent source of truth. Okay, so those are all of the applications. Now I'm going to talk specifically about some of the approaches that we used in designing ER² and what worked and what didn't really work. So since Think Data Works is a company and we have clients that want to use our ER system, we had a couple of constraints for the product that we wanted to build that wasn't necessarily faced within literature. So the three main things that we wanted in our ER system was that it would be accurate, it would have good performance metrics, and it was also scalable. We started our entity resolution project earlier this year, and we began by building off of academic findings. And so many of these try to use semantic matching. And while this maximized our accuracy metrics, it also it wasn't the most scalable or the most computationally inexpensive. So examples of things we tried are like a fast text model to enable semantic word embeddings, an HNSW, which is an approximate KNN algorithm, and then different classifiers in a Siamese network to disambiguate between potential matches. However, like just loading all of these models requires a lot of memory, and it didn't produce something that was computationally inexpensive or scalable for our clients' real-time ER needs. So in our later attempts and our current proof of concept, which is ER squared, we tried more traditional natural language processing techniques. And while these were more basic, they actually turned out to be close in accuracy, but way more scalable and less memory intensive. So things that we tried, we currently use a classifier to determine which entity type the specific user wants, and then we use different tokenization and pre-processing techniques that optimize for the structure of that entity. And then finally, we use different matching functions, the main one being term frequency, inverse document frequency, and we compress our representations of the specific entries using sparse matrices. So to give some numbers, we ran, one of the data sets we ran ER squared on was the DBLP ACM ER data set, and we scored an F1 score of 97, which is just a bit under Magellan, which is the current leading ER system in academia, which has an F1 score of 98. The last thing we did was we parallelized our matrix computations using Spark clusters, and then applying a stress test, we could deduplicate a data set of 4 million entries, which translates to 16 trillion comparisons, since it's an O(n) squared problem, in 17 minutes using 128 cores.
We talked about maintaining master records is important to create a holistic view of information. However, humans still need to be involved to really understand the underlying semantics, and so that they can get useful insights. So we decided to take an extra step forward to add more context by using schemas to define entities. So schema.org is a community founded by Google, Microsoft, Yahoo, and Yandex, with a mission to promote a shared schema for structuring all types of data. Schema not only allows us to better standardize information for entity type, but also it provides meaningful relationship between entities so that information is ready to be consumed. We've decided to follow and align with the industry standard, and here's a subset of entity schema that we're starting with. So organization here is an entity type, and its property address affects another entity type called postal address. And entities can share and inherit properties from its parent entity, which is usually more abstract, like thing here. And entity understanding is the key for both efficient master data management and for knowledge transformation. This is especially true when you're dealing with a large number of data sets that are constantly being updated. While building master records only requires understanding entity type, but building knowledge graph requires multi-stage classification of both entity type and its property mapped across dataset attributes. And we started an annotation service to collect labels for datasets, open datasets based on the latest schema definition. So here's an example of entity understanding on a dataset. So for each dataset, we're given unstructured data such as title, description, together with structured data like column names here and sample rows. We want to predict its entity type and relevant property mapped onto each column attribute. So city is predicted as a postal address with property address locality. If there are multiple entities found from a data set, this example, we additionally have to predict the relationship that explains the relationship between two different entities. such as postal address and person. And in this case, based on the schema, the property is address. So here's another view of how data gets transformed into knowledge. A string alchemical operation is found from data, but it has no context. After multi-stage classification, alchemical operation is now known as organization with a property legal name. And then related entities with property gets extracted from a data set, and it forms a local knowledge. With entity resolution, knowledge gets aggregated and consolidated, forming this knowledge. So this year, we started the new project called Marvin to create entity understanding engine based on open data. And our main goal for Project Marvin is to make open information more accessible to the public. To do so, we're building automatic data knowledge transformation pipeline. And this will help people to obtain potential insights much faster in 3 different ways. 1, users can use their own data to query against the open knowledge service. 2, user can use natural language to ask questions to get relevant entities. 3, user can also get relevant source data for more detailed view. With open knowledge, we believe that we can solve inefficiency in data science and help our data scientists be data scientists. And if you found this problem interesting, our door is always open. Thank you.
Have you ever had to unravel it when you realized that you thought they were the same when they weren't?
There was definitely a lot of debugging in the process, for sure, and looking at the results, especially. So I think getting labeled data for the PR problem is particularly difficult, just because it's like a smaller problem within NLP, like Hoyoung mentioned. But when we ran a lot of benchmarking, there was definitely a lot of debugging and working on, it was like balancing between accuracy and recall. So sometimes there were incorrect matches, especially when you take, like the way we did it, we tokenized a lot. So sometimes similar words would be matched. And it was about like tweaking our hyperparameters and like our thresholds to make sure that we were optimizing for like both accuracy and recall.
Were there any techniques that you used that cut down your complexity from n squared?
So right now we are focused on like distributing search space, but we do try to work on like cutting down using the blocking mechanism within the search space, hashing mechanism, but yeah, it's ongoing.
It looks like you guys deep dive into the properties directly using NLP, but are you guys leveraging any metadata of the original data? For example, if it's a float, if it's other like text or other formats like categorical features, are you leveraging those metadata?
Yeah, we are. Okay. That's done in data management time, and we are using those.
So when you built the knowledge graph, did you use any graph database?
Currently, we're trying with Janus graph.
Is there any way to say that, for example, the machine learning stuff that you do is optimal or near optimal, is that kind of stuff? So, for example, if you have some data and that it's a huge database, right? And you already know that there are this much number of repeated items and you want to remove them. So based on the algorithm that you have, how many of those items are removed and stuff like this. So I'm more interested in to see how optimal we are with this kind of algorithms in terms of repeating items, removing repeated items.
We haven't benchmarked that. All of the benchmarking sets that we did were to think. So you're asking our accuracy metrics on deduplicating across data sets, right? So data sets, like specifically like the DBLP ACM one, that one looked at linking records. I don't think we benchmarked on any that were specifically looking at deduplicating. I think the higher level application that we were focused on was linking, just because the actual deduplicating isn't as I don't want to say meaningful, but it wasn't like the application we were focusing on, because linking enables us to build a knowledge graph, if that makes sense. But I mean, hopefully we will benchmark in the future on deduplicating as well.
Thank you.
Have you guys done anything to address transitivity? I mean, I've personally worked on entity resolution before. So if you have 3 entities and you find A equal to B, B equal to C, but if it's a pairwise comparison, it's not guaranteed that A and C are equal, correct? That's called transitivity challenge, and I'm wondering if you guys have done anything addressing that.
So since I'm not fully sure I'm going to answer your question correctly, but because of the way that it's actually implemented and we're using graphs within it, if A and B are seen as a duplicate, they get an edge, and as to indicate that they're duplicates. And then if B and C independently are also seen that way, then they get an edge. And then within the graph database globally, A and C are linked through B. So that's how we construct the groups of our nodes that we see as one entity. Does that answer your question?
Partially, but I mean, they have edge, and do you actually apply community detection afterwards, so they are in the same communities, or they're sort of considered intact in the same community, they're the same entity?
We not focus on detecting communities at this point,
Okay.
but we do have reference to the duplicates so that we can traverse. Thank you.